Right, so we can go ahead and get started today for you guys. Dean, if you can go to the next slide for me today. And so the speakers on the webinar today are going to be myself. My name is John Stevens. I'm the North America Sales Manager for our Astera Earthworks solution. And I'm also joined here today by Mr. Gary Eaton, who is the Executive Vice President of Operations at Astera and is formerly the Director of Operations and Maintenance at the San Diego County Water Authority. And lastly, we do have Jonathan Lynch on the call as well today with us, who is our lead geotechnical engineer here at Astera. And so, again, thank you guys for joining our webinar today. Going forward into the agenda on the next slide, first we will discuss L Band synthetic aperture radar, or SAR for short, really for proactive infrastructure monitoring. Then we'll go into the associated benefits of the Astera Earthworks solution when it comes to safety, operations, and also asset life. And then we will go through a case study focused on the Tarrant Regional Water District and their use of the advanced satellite technology to monitor one of their dams in their service area. And then lastly, like I mentioned, we will open that up for some Q&A for you guys as well. Now, moving forward to our overview of L Band synthetic aperture radar for proactive infrastructure monitoring. So regarding the earthworks process itself, and so regarding the Astera Earthworks process, it is mainly a three-step approach for us here at Astera. And so we have the view where we utilize a high orbit satellites that carry the large L band synthetic aperture radar sensor. And that sensor is then utilized to attain the data quickly. And then lastly, we utilize our algorithms to really analyze that data to locate areas of where we see high subsurface moisture around these critical assets for you guys. And so moving forward to the next slide here today. And so why use satellites for infrastructure monitoring? Firstly, satellites provide really continuous and uninterrupted scanning, which can operate day and night, and also is unaffected by cloud cover, rain, fog, or smoke as well. Satellites also provide us with a very large acquisition area. And so where we can usually collect data at a consistent resolution across approximately 1,400 square miles in coverage, just depending on which satellite we're using for the given application. And then by using satellites, we can acquire the data remotely and collect the data non-intrusively as well. And so this requires no on-site equipment, no field installation, and no maintenance as well on this technology here. Now, moving forward to the next slide. Regarding satellites, there are many different technologies, sensors, and bands that can be used to observe different signals. For example, in the slide here that you're seeing, you can use a multispectral technology to observe really environmental responses to increased areas of water availability. INSAR provides it really observes ground deformation or subsidence signals and then we also have pulsar or polar metric SAR, which then observes subsurface moisture and looks for soil moisture anomaly signals within the subsurface moisture there for you guys. Now, each approach can really capture a different aspect of the exact same underlying phenomena, just really at different stages of their life cycle right there. And so going forward, why do we use L band synthetic aperture radar here at Astera? So you can go to the next slide for me, Deanna. And so really with L band synthetic aperture radar, the main reason why we use it is that it is a very elongated wavelength. And so with L band, it has roughly a 9-inch wavelength, which gives us the ability here to penetrate the Earth's surface, but not only the Earth's surface as well. We can actually penetrate through vegetation, any surface materials, and also shallow ground layers as well. Now, L band also is very sensitive to water. And so it can detect differences in dielectric constants to water within soil. And it is also ideal for linear and hard to access assets since it provides uniform coverage of long, complex networks such as levees, canals, roadways, and covers areas that can't be either safely or easily inspected by ground crews as well. And go forward one more slide for me, Deanna. All right, I did get a ping that we're having some audio issues. Just wanted to check real quick. Deanna, are you guys hearing me okay?
I can hear you, but audience members are saying they can't hear audio. Audience members, can you hear us now?
Get some thumbs
I'm
up
getting
there.
some
So
thumbs up.
yeah,
Okay.
so I'll continue on. It might be just some kind of an audio settings. If you guys go down to the bottom, if you're having some audio issues on the right-hand side, those three dots down there, you should have some audio settings. It might just be toggled on and off to a certain different output for you guys there. What we'll do as also at the end of the webinar as well, we'll send all this information over to you and a recording for the webinar as well for you guys. Alrighty. So moving forward into really SAR frequency, it really determines what you can see in different bands. Of course, allows you to see different stuff and penetrate through different materials and at different lengths as well. So to give some further insight into, of course, why we utilize L band in comparison to other bands such as an X band or C band, where we can look at this diagram right here. And so, as I mentioned on the last slide, L band really provides us with the best penetration out of the bands, given that long wavelength, about that 9-inch wavelength right there. And so, with L band, we can penetrate the Earth's surface to see those subsurface moisture anomalies. With X band and C band, the penetration is really greatly influenced by the surface materials, making it difficult to see subsurface conditions with those bands. And so, X band, C band may be great for, say, agricultural applications, but if we're looking really to go and find subsurface, say, moisture or seepage, or potential signs of internal erosion, that's really where L band has the expertise in. And so, really, with the use of L band, we're able to penetrate through those subsurface conditions, the surface materials, vegetation, really anything associated to that as well. And so now I'm going to hand it over to Mr. Jonathan Lynch, our lead ground geotechnical engineer, who will take you through some of the geotechnical engineering considerations for both dam and levee safety right here. So Jonathan, take it away.
Okay, so yeah, I want to talk about just the basics of geotechnical engineering associated with dams and levees. If we can look at the next slide on, please, Diana. And again. So we all know what a dam looks like, but let's just put it down into its schematic here. So we've created a artificial barrier across a valley here using earth. So that earth is compacted in layers and then built up in benches to a certain height, and then the reservoir is flooded behind it. But in accordance with this, you have potential zones of weakness due to construction. You've got the abutments on the left-hand side, the right-hand side, and if the material's not keyed into the abutment correctly, there could be potential zones of weakness there. Through most dams, you'll have an outlet which is fed from a principal spillway. So there'll be a pipe going through the body of the earth dam, and again, if the construction around that pipeline has not been done correctly, then there's potential zones of weakness there, through which water could start to seep and migrate to the downslope side. And in most cases, for earth dams, you'll have a grassed or riprap type cover on it. Certainly not a forested or wooded face. So we're generally looking at grass slopes, which is perfect for L band penetration. So if we can move on to the next slide, please. So this next slide is just looking at a typical cross section. Now, all dams vary in construction. There's a very schematic one. That's your earth dam holding back the water on the upstream side, and generally this will be constructed over an impermeable foundation. It could be a clay base, a silt base, or even rock. It could even be artificially treated with grouting to improve that foundation. And generally what will happen over time is the upstream water will start to migrate down through that earth dam. The earth dam, because it's made of soil, will contain pores, and the pores will gradually fill up with water, and the water will flow down to the downstream side due to the difference in hydraulic head. And that occurs in every dam, so every dam effectively will leak. The rapidity of that leak, generally we hope, will be centimeters per year. That's a typical rate for a well-constructed dam. But if you've got meters per day, then potentially you're looking at particular problems with that. We can go to the next slide, please, Diana. And the next one. So some modern dams, to alleviate the buildup of poor water pressures caused by this natural seepage in the dams, will contain drainage blankets. There's one here shown at the base of the dam. So that's removing that hydrostatic pressure at the toe of the dam there and reducing it from the face of the dam. So all that seepage water is getting contained into the drainage blanket and led away. So nothing's escaping to the face of the dam. these drainage layers can be horizontal, like shown here. They could be subvertical. They could be abutted against an impermeable core, which I'll show in the next slide. So we can move to the next slide, please. So these impermeable cores, in modern dams, they're generally constructed out of clay. It could be asphalt, or could be a bentonite core. And this really reduces the impact of that natural seepage. That phreatic line is impacted dramatically. You see there the phreatic line has gone subvertical, so that's slowing the water down completely. It might go into a drainage layer which is horizontal, and indeed you may have a drainage layer which abuts the core on the downstream side, so that intercepts any seepage higher up in the core and reduces the potential for seepage to escape to the face of the dam. So typically a core will behave like a modern day landfill cap. The landfill cap is usually constructed out of either geotextiles and geosynthetic layers, or indeed a certain thickness of an impermeable clay core with a very, very slow permeability in centimeters per year. So we can go to the next slide, please. So what happens when that impermeable core is not working, or certain things in the dam construction were imperfect during construction? What I mean by that is the soil is compacted in layers for the construction of the dam. A certain amount of quality control has to go into that to ensure that the materials being brought in are the correct materials, that they've been placed and compacted to the correct density, and that there's certainly no foreign bodies within that material. So if you can imagine, if there was 5 meters of clay and then there was a mistake and somebody brought in a layer of sand by mistake and it wasn't picked up, that's going to cause a problem. And indeed, pauses in construction for several weeks due to downtime or whatever it may be. There could be significant drying on the upper surface of the layer, and if that's not then recompacted and done in a correct manner before constructing the next layer, there could be imperfections in the barrier, and that could cause potential migration of water and pathways to develop. And you'll see in the lower part of the diagram here, there potentially you can get seepage beneath the dam through the foundation, and that can emanate downstream of the dam, meters from the toe or several meters away from the toe. So in inspections, you're not just looking at the face of the dam, you're looking certainly downstream as well to see if there's anything bubbling up from the soil. And the lower face of the dam here, I'm indicating there's potential seepage which is coming out at the dam face. And in your inspections, you may be looking for things like a deepening in color of the vegetation or more growth of vegetation. You may find that the soil is softened. You may even see water at the surface. But that may be occurring. But what if you see things like staining? If you see water flowing, if you see discoloration in the water, then that's a significant problem. And you're looking at an issue there which is already developed potentially into water migrating like at meters per day sort of rate, which is a problem. The higher up seepage, which is indicated, has not yet reached the surface. These are areas which are of concern because, you know, if they do reach the surface, they can start to accelerate, and that acceleration of water can bring particles out of the dam. It can lead to piping, and then it can lead to further erosion, and it can lead to catastrophic failure. And these are the sort of things that the L Band SAR being able to see below surface. We can see where areas of high moisture are below the surface of the dam, approximately 0.5 meter to 1 meter. And that gives you a huge element of time in being able to investigate and mitigate. And the reason we need to mitigate, obviously, go to the next slide, Deanna, we don't want to end up with situations like we have in this. This is a dam in Tasmania. And you can see there the seepage is in several stages. Sort of in the center of the diagram, you can see the seepage just starting to flow. There's an area there where the flow is starting to get quite severe and piping is developing. And over to the right, piping has turned into erosion. And also further to the right, you can see seepage starting on the abutment. So again, the abutment, potentially that was not constructed correctly. They didn't step it in properly and didn't seal it as the way forward. And you really want to sort of avoid getting to this situation, and because you obviously have, in the next slide, you get a catastrophic failure, and that is obviously disastrous, not only from the safety point of view, but lives at stake, compensation, etc. So handing back to you, John.
Thanks, Jonathan. We're actually going to hand it over to Gary to go through some of the benefits today of satellite monitoring for increased efficiency and safety there. So Gary, feel free to take it away.
Great. Thanks, John. So let me start with probably one of the most important points, and that's that Earthworks is not just another data set. It fundamentally changes how infrastructure is managed. It gives operators the ability to detect geotechnical risk months, potentially even years, before it becomes visible in the field. This has three very practical impacts. The first one, it allows you to prioritize inspections so your teams are focused where risk is actually forming, not spreading your assets across the entire asset. Second, it reduces your operational costs and improves your efficiency because you're no longer inspecting everything. And then third, and most importantly, it helps extend the asset life and improve safety by enabling earlier intervention at a lower cost. So in simple terms, Earthworks changes the inspection strategy. It helps reduce risk and extends asset life. Okay, next slide. Okay, so let's talk about trends a little bit. So visualizing soil moisture trends, either increasing or decreasing soil moisture, is one of the most important capabilities that Earthworks provides to you. A static map tells you where conditions are at the time today, but failures don't happen because of a single point in time. They happen because conditions change over time. And what Earthworks does is detect those changes over time. Shows you where moisture is increasing, where risk is forming, even in that area that hasn't maybe reached a critical level yet. That allows you to distinguish between areas that are stable and areas that are deteriorating. And that's a critical shift because static high moisture tells you where you already have a problem, but trends tell you where that problem is developing into something you need to address. And that's how you move from really a reactive phase into a more predictive and proactive response. Next slide. So what does this actually look like in practice? So it's a pretty straightforward workflow. The owner defines the area of interest, or what we call an AOI. And so that may be a dam, that could be a levee, that could also be a road in a corridor. Earthworks maps that subsurface moisture across the entire area. And when you look at this slide, you can see kind of a moisture map up the very right square box, very top square box. So we map that entire area, and then we highlight zones of elevated risk across that asset. And we use a predetermined grid pattern. So we essentially lay a pattern over the top of that. And those grids are then categorized by severity. So we provide alerts or alarms based on that soil moisture content within that grid. And those become the basis for action. So your alerts are shown in yellow, your alarms are shown in red. So instead of a broad routine inspection, operators can now focus their field resources on those specific locations that matter the most. From there, inspections are targeted, mitigation decisions are made earlier, and then monitoring becomes more focused for your teams. The outcome is fewer surprises, more efficient inspections, and greater confidence that the risk that you are encountering is being managed proactively. Okay, next slide. All right. So prioritizing inspections. So this is where Earthworks changes day-to-day operations. So our output is really very simple. You got red alarms. Those are areas that you want to inspect. Likely you want to inspect those immediately or very soon. Yellow areas are alerts. Those are monitored, and you may schedule those at a routine inspection, but areas that need to be monitored closely. So the key factor here really is around trends. If an area is getting worse over time, it moves up in your priority list for inspections, even if it's not yet in an alarm condition. So instead of inspecting 100% of the asset with the same level of effort, you're now looking at maybe 5 to 10% of that asset, where you can really zero in on those alarms and alert areas. And that's a significant shift in how inspection resources are allocated, and it's where a lot of the operational value of earthworks comes from. Next slide. Okay, so one of the most important outcomes of this approach is certainly it's extending the asset's life. Most infrastructure risk starts below the surface with moisture. The moisture leads to seepage. That seepage in turn leads to erosion. Erosion then eventually leads to structural degradation and failure. So the problem is that by the time you see visible signs, that degradation process is already well underway. So earthworks allows you to intervene earlier, before that progression accelerates. That means preventing internal erosion, reducing slope instability, and avoiding long-term structural damage. With aging infrastructure, and particularly as we see more extreme weather patterns, that early intervention is becoming more and more important. So earthworks doesn't fix infrastructure, it helps prevent it from degrading in the first place. And next slide. All right, so this slide kind of summarizes what I've been talking about. So in stage one, risk begins below the surface, where traditional inspections can't detect it. So over time, moisture increases and patterns develop, but there's still no visible signs. In stage two, that's the window where earthworks operates, and that's where we start to detect those changes months, maybe even potentially years in advance. In stage three, eventually you start to see those surface indications, whether it's seepage or wet areas or even slope changes. And at that point, you're already in a reactive mode. And if conditions continue on, then particularly to stage four, you reach a failure risk condition. And certainly having to address it at that level is the ultimate in expense and impact to downstream. So what earthworks does is shift detection back into the earlier phase, stage two, when you still have time, options, and can address the issue at the lowest cost. That's the difference between really managing the risk and reacting to it. So with that, John, I'm going to go ahead and turn it back to you so you can share a case study from one of our existing customers.
Amazing. Thank you, Gary. Appreciate that great insight there. And yeah, as Gary was mentioning, now I'm going to go through really a real world example for you guys of Astera Earthworks in action. And so this case study is focused on our work with the Tarrant Regional Water District and specifically around their Joe B. Hogshead Dam here. And so with really what Gary was mentioning earlier, and really the true value with the trend analysis here. And so what Tarrant Regional Water District decided to proceed with on their dam was initially they did 4 scans throughout the year period covering that dam. And now we're looking at about 2 scans a year moving forward. And so really some benefits there, of course, big time on the trend analysis for you guys, so being able to see where those grids are either getting wetter over time, getting dry over time, and being able to mitigate potential failures associated to those. And so with Tarrant Regional Water District, they were for sure facing a few challenges with the dam, which pointed them really to look at advanced technology to go out and monitor the dam for them. And so very similar to, honestly, most of the dams in the US right now, as I'm sure a lot of you are aware, really aging infrastructure is a huge challenge. And so this dam specifically was nearly 60 years old and also has a high hazard rating with a population and critical assets located downstream. Now, the dam also required periodic inspections that required significant staff time. So with all these challenges, TRWD was really looking for a more efficient way to monitor this critical dam, which is why they decided to utilize the Astera Earthworks solution to really get that done for them. And so the Astera Earthworks solution for Tarrant Regional Water District really provided a soil moisture map that revealed potential areas of seepage along that dam, and multiple satellite images and analysis of that dam allowed TRWD to, like I mentioned, track that dam behavior through the trend analysis and track those potential seepage patterns over time, where they were able to actually confirm certain previously known areas and also several new areas that needed further inspections. Now, TRWD would inspect the alerts and alarms that were found using the Astera earthwork solution, as Gary showed you guys here a few slides back. And so really those actionable sites that we're able to provide to you guys. So we see the entirety of the dam and analyze the entirety of the dam, but we focus on those really critical areas where we already see that very high soil moisture accumulating below the surface of that dam right there. And so, excuse me. One instance that they were able to locate was actually a potential natural spring to the right of the dam that the utility was not aware of at the given moment, or aware of previously or at the given moment, and also located known areas of the central part of the dam where relief wells were located to. It's really speaking to that technology that we're able to, one, see a lot of different assets and inside the asset for you guys, whether it be the drainage layers, any relief wells, anything like that, but also any ancillary stuff as well, such as potential natural springs that might be influencing some seepage on that area as well for you. And so with the good collaboration between the TRWD engineers and their field teams, they have now really been able to move to a more efficiently monitor that dam, more proactive, more preventative kind of maintenance on that dam for them, and make a lot more informed decisions at the very early stages of the potential issues right there. And so that really is name of the game with earthworks, is catching those issues early on, like Gary was mentioning, being able to have time to mitigate those potential failures, and just have more time to make informed decisions on potential repairs and or other further inspections that might be needed on that side of the things. And so I know we have a few kind of minutes left in terms of the presentation. Anything, I know we're kind of ended a little quick here today, but I just want to put our quick contact information up on the slide for you guys today. And so you have Gary, Jonathan Lynch, and myself, John Stevens there. If you guys want any additional information on anything we showed you today, the case study itself, the earthwork solution, more than happy to provide more personal or more in-depth demos at any time for you guys. So feel free to reach out at any point. And then just finally with the last kind of housekeeping item here for you guys, since I know we had some technical audio issues, so I do apologize for any audio issues that did occur at the start of the presentation for the audience here. We will be sending out a recording. We will make sure the audio is all good on the recording for you guys to send over to you. That should be in your inbox here before the end of the week. So we'll get that over to you guys. And if you want kind of just a more personal presentation on the webinar itself, please feel free to reach out to myself, and I'm happy to get that going for you guys anytime. And so now is the time we're going to open it up for some questions and provide those answers back to you guys as well. And so, like I mentioned previously, you do have a spot at the kind of in your toolbar there to go and ask questions. Be that little kind of question mark down there. So feel free to input any questions you guys have. We'll be sure to get those answered for you guys right away. If we, for any reason, don't get to all the questions, we will follow up with an email for you as well with the answers to those questions there. So I'll give you guys a minute or two to put some questions in there if you have any, and then we'll go ahead and get started with those. All right, so we got a few questions coming in here real quick. So I'll start us off real quick. Got a question here actually probably be best suited for Gary. And so in terms of kind of the ideal interval of capturing the images, is there kind of what is that ideal time, Gary, for capturing the images, that interval where you would see the most benefit for the earthwork solution?
No, that's a great question. Typically, we defer to that asset owner. So, for instance, if I know I'm going to be storing water, say at the end of the spring period for summer, I want to maybe image it when I'm at the highest water level. And then if I'm maybe bringing my reservoir down because of quagga mussel, and I want to do some desiccation of those, and so I'm going to bring that water level down. I might want to image it then. And then also maybe operational issues, like I've got a large amount of yield that came in very, very quickly due to storms or something like that, hurricanes we've had. So we really talk to the owner and kind of work with them and understand their seasonal fluctuations, and then also operational changes. In some instances, for instance, the one I managed for a while had a hydro generation capacity. So there were specific times of the year where you would bring the water down, or you might have it higher. So it's really up to that operator and us to kind of have that conversation.
Absolutely. Thanks for that, Gary. Appreciate that. Got a question here, and I can get this one answered for you. And so, what kind of lead time do you need for your analysis? And so, with satellites, one of the benefits is very frequent coverage and also large area coverage as well. And so, from notice to proceed, and when you guys would want that image, I would say usually give us about a 3-week turnaround time on that side. I think it's a 3-week notice, kind of when you guys want that data to be in hand. Depends on where the sat is. Most of the time we get it to you quicker. Sometimes it might be a little longer than that, but usually always before a month time frame for you guys there. And then also got another question here that I can get answered for you as well. And so what is the resolution or the pixel size of our satellite imagery provided? And so resolution about 1,400 square miles. The pixel size itself, roughly about 18 feet. Um, Depends on kind of the satellite we're utilizing, but roughly around that on average. It's about 18 big pixel size there. Amazing. I'll have a question. Jonathan or Gary, feel free to answer this one. Does high grass affect the resolution of the ground moisture?
Well, yes, of course it does. But I mean, if you're looking at, as John explained in the earlier part of the presentation, if you're looking with C-band, for example, C-band will basically be looking at the surface in the upper sort of 3 to 5 centimeters. So water on the grass at that point will affect the signal return, and you'll get an indication. You'll get an indication of wet grass effectively. With L band actually penetrates the surface and penetrates the soil by a distance of 0.5 meter to 1 meter on average. Generally, we're comfortable with that, and it depends on the soil density, the soil type, the actual vegetative cover, etc., how deep that penetration can be. So yes, the answer to your question, does grass, high grass affect resolution? Sorry. Yes, if it's wet, you'll be seeing high moisture. But for L band, the height of the grass really doesn't affect us that much.
Thanks for that, Jonathan. I did have another question there. Just to reiterate to Wes, and I had a good question there about the L band signal penetration. Yeah, roughly, it really just depends on the soil conditions at that point. But I would say on average, you're getting about 1 meter to 1.5 meters on that side of things. Sometimes we can go deeper. Just depends really on the soil conditions that we're looking at that point. Alrighty, got another good question here. How far back does satellite data go for you to be able to do a progressive analysis? And so right now, everything that the Astera solution does is really based on task. And so we use a few commercialized satellites. So everything's based on task. Now, if we have data from, say, previous projects, we also do a lot of work on potable water and wastewater pipelines looking for leaks. And so we do have a good amount of imagery already spaced throughout the U.S. and the world as well. And so if we do have imagery already covering that area for you guys, we might have that from different points in time we've been doing business for the last 10 years. So might have it going back that far, but it's not guaranteed. And so if you guys wanted me to kind of look closer into that, I can for sure do that on another call with you guys and kind of look to see if we have any historical imagery as well. But for sure, big benefit in some historical imagery, for sure being able to go look back at potential trends back then leading to now. And so yeah, there's potential there, but it's not kind of guaranteed at this time. Alrighty. And so do have a quick question here, and I'll toss this one over to Gary right now. And so kind of a two-step question for you here, Gary. First one, can you see through snow cover? And also, is this real time?
Yes, we can see through snow cover. However, we cannot see through ice. So we had a project up in Sweden, if I recall, Levee Dam, where we imaged they suspected a leak, and we also sent a team out to basically do some ground verification. And before they got out of the truck, they could see the difference in the snow. It was discolored and it was wavy, didn't have the same texture in the area where we thought the leak was. And we also saw that ice didn't form at the edge of the dam where the suspected leak was. So in answer to your question, yeah, we can see through snow. But if it's got a very solid ice base underneath it, then no, we'll get stopped at that ice level.
Amazing, 100%. And second part to that question, real quick for you, Gary, is this real time? So is this their earthworks real time?
Well, the devil's in the details. What are we describing as real time? Now, what happens is you'll define that AOI, and then at that point we will task the satellite to take the image, and then there's the processing of that image and the use of the algorithm and so on before we get it back to you. So can we do it real time? No, but we are taking the image at a specific time, and you'll get it about 3 weeks later with the analysis, as John explained.
100%. Thanks for that, Gary. Yeah, just to reiterate there. Yeah. So really everything Astera does is we take an image of the asset of the system, really at a snapshot in time. And so you have that data from that specific point in time. And then we always for sure recommend kind of multiple scans of that asset to really get you guys that great trend analysis that we can provide to you back as well.
Yeah, I think there's a tendency to think that we need to have it real time, but in reality, the asset is not deteriorating in most cases that rapidly. So we can take that image, and particularly when you look at trending, we're looking for that change over time, and so we get a good baseline, start to monitor it over time, and then we are able to react and respond to it as early as we possibly can, reducing cost.
100%. Absolutely. Thanks for that, Gary. And looks like I got one last question here from the audience. I'll toss this one over to Jonathan to give some more kind of geotechnical advice to it. Is this affected below the lake water line, and if so, how deep?
Below the lake water line, so below water. No, we don't see below water. Effectively, water will act as a mirror. We will receive no signal from below the water line at all. So certainly not affected of looking at upstream effects on the face of the upstream dam. We can't see that apart from above that water level. So shallow sort of surface or potential surface failures at the crest of the dam, we can see that. But as soon as you go beneath water, we're unable to use the signal.
Amazing. Thank you for that, Jonathan. Alrighty. Looks like we're pretty much at our time here today, guys. And so I really appreciate the time you guys took today to attend our webinar. If there's any questions that come through after the webinar, I'll be sure to get an email out to you guys today to get those questions answered for you pretty quickly. And so, like I mentioned again, really appreciate you guys taking the time to join the webinar today. Gary, Jonathan, thank you again for joining me on the webinar today. Great questions from you guys. I'll be sure to get those answered for you before the end of the day today. And just as a quick reminder, we will be sending over a recording for you guys of the webinar itself in case you wanted to have it on hand or view later or send to any team. But yeah, like I mentioned, really appreciate the time today, guys. Hope you guys have an amazing rest of your week. I look forward to hopefully crossing paths with you guys in the future. So thank you very much. Have a great rest of your day.
Thank you.